Good evening. We have today lecture number 6. We are with design. Already we have gone through analysis and now we are with design. And in design, we are going to be with second part. In first part, we have gone through problems which are based on clause number 8.2.1. So 8.2.1. This clause is related with VU less than 0.6 VD, where we are going to say bending moment predominant. And second, we have that is clause number 9.2, and this clause we will use when we have VU greater than 0.6 VD. In this clause 9.2, we have this clause that is on page number don't remember page number. So we have this clause number 9.2 which we have to use, and by using this clause we are in position to solve this problem. So in this we are going to use this part to solve the problem. Now we will go with problem. So we have design a laterally supported beam, subjected to a factorial bending moment, of 155 kilonewton meter and shear force of 200 kilonewton. Take Fy equal to 250 Newton per mm square. Now we will solve this. So we have step 1 given data. Step 1 given data. So this is solution. Given data, and in this we have given shear force equal to 200 kilonewton, bending moment equal to 115 kilonewton meter. Then Fy 250 Newton per mm square. And we have beam laterally supported. So laterally supported, we have two clauses, 8.2.1 or 9.2. Now we have step 2, section modulus required. Now already in last video, we have seen how we have modified this formula. So I will not explain that. You can see last video, and from this you can see how we got this formula. ZPR equal to mu upon gamma mo divided by Fy. Now mu we have 115 into 10 raised to 6 multiplied by 1.1 divided by 250, and from this we will get this value 506 into 10 raised to 3 millimeter cube is equal to 506 centimeter cube. Then we have step 3, selection of section. Step 3, selection of section. Selection of section. So we have select ISLB 300 at 37.7 kg per meter. Now, once we have selected this section, our analysis step starts. So we have first properties of section. Properties of section. So we have H 300 mm, H equal to 300 millimeters, BF 150 millimeters, TF 9.4 millimeters, TW say 6.7 millimeters, ZPZ 554.32 into 10 raised to 3 millimeter cube, and RYY is equal to 28 millimeters. Now we have step 5, classification of section. Classification of section. And in this classification, we have B upon TF. B upon TF is equal to BF by 2 upon TF. And we have 150 upon 2 divided by 9.4. And this is equal to 7.98 less than 9.4. Therefore, flange is plastic. Table 2. I am not repeating this, page 18. And why BF by 2? You can go page 19. Then we have D by TW. So we have H minus 2TF upon TW. So H we have 300 minus 2 into 9.4. 300 minus 2 into 9.4 divided by TW is 6.7. So equal to 41.97 less than 84. So we have web is plastic. And therefore, section is plastic. Therefore, section is plastic. And therefore, beta B is equal to 1. Then we have next step, that is step 6, shear strength. Step 6, shear strength of section. And this will decide which clause we have to use. We have to go for bending moment predominant, or we have to go for combined loading. So clause number 8.4, page 59. We have VD equal to. Now these all already explained in last videos. So I am just going to write down the values. So we have 300 multiplied by 6.7 into 250 divided by root 3 into 1.1. And we will get 263.74 10 raised to 3 Newton, 263.74 kilonewtons. And then we have to find 0.6 VD. 0.6 into 263.74, which is 158.24, which is less than 200 kilonewton, and therefore use clause number 9.2, which is for combined loading. combined loading. Then we have to go for clause number 9.2 in step 7. So we have this value of formula MdV. Now we can write bending strength. We have formula MdV is equal to MD minus beta in bracket MD minus MFT. Now MD we know we have beta B ZP ZFY upon gamma M. Value of beta formula 2VU upon VD minus 1 whole square, and MFD, this is bending strength due to flanges only. Bending strength due to flanges only. We have to neglect due to web. So now first we will find MG. So we have beta B1. We have ZPZ 554.32. 554.32 into 10 raised to 3 into 250 upon Fy gamma mo 1.1, and we will get value of MD 125.98 into 10 raised to 6 Newton millimeter. 125.98 kilonewton meter. Then we have beta. So formula already I have written over here, 2VU upon VD. So we have 2 into VU is 200. Upon VD, we have 263.74. VD we are interested. Minus 1 whole square. And we have this value 0.267. 263.74 we have over here. Then we have to find out MFD, and we have to use formula beta B ZPFD into Fy upon gamma M. Now ZPFD means we have to find ZP of flanges only, and for that we have to draw this diagram. And then we have this value, that is BF, and value of BF we have 150. Thickness of flange we have 9.4, and we have to take at center. So we have 300. So we have this value 150, and we have to find value from center, and this will be 150 minus 9.4 divided by 2, and that will be twice. We have to take moment of this area, and from this we will get ZPFD equal to 2 times we have on both sides area of flange 150 into 9.4, and Y bar, that is 150 minus 9.4 divided by 2. This value we have 409.75 into 10 raised to 3 millimeter cube. And then from this we will get MFD, that is 1 into 409.75 into 10 raised to 3, 250 upon 1.1. And from this we got this value as 93.12 into 10 raised to 6 Newton millimeter equal to 93.12 kilonewton meter. And then we have to find out mdv, which is equal to md, and which is equal to md minus beta in bracket md minus mft. And md we have calculated 125.98 minus beta we have calculated 0.267. md value we have 125.98 minus mfd 93.12. And then we will have this value of mdv 117.21 kilonewton meter, which is greater than 115 kilonewton meter, which is value of mu. And therefore we have design strength greater than mu, therefore safe. So likewise, we have to solve these problems on design of beam. And this is separate, I already mentioned, that is related with clause number 9.2. So now we will stop here only. Thank you.